Okay, this is a continuation of the previous lecture. So just to remind you, we were collecting the statistics of electrons that were watched. So I'm watching the electrons. Which slit are they coming from? Whether they're coming from slit 1 or they're coming from slit 2. And what I can do is that I can collect the statistics here, click, 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 where I also know not only at what point of the screen they are hitting, but I also know from which slit they pass through. So let me draw the histogram, and from that the probability distribution of the electrons that pass through slit 1. Let me call it P1 prime because they are the ones which are watched. So P1 prime are the electrons coming from slit 1, and I have similarly P2 prime electrons coming from slit 2. How do I know? Well, because I am watching the flash of light, and if I add these, I take a statistics of all the electrons coming, irrespective of which slit they are coming from. The net probability is going to just add up. It's going to be P prime, and in this case I'll have P prime, maybe I should call it P prime 1 2. P prime 1 2 is equals to P1 prime plus P2 prime. So it's kind of neat that when I watch the electrons, I have the addition of probabilities of the electrons taking the two alternatives. What we can do is that we calculate the probabilities. What's the probability? So this is the gun G, this is the screen S. What's the probability of GS? The probability that an electron started from G and ended at a certain point S. Well, this is probability G A1 S, where this was A1, A2, plus probability G A2S. So let's pause here for a minute. What's going on? Well, what has happened? We have actually made the paths distinguishable. And remember, for distinguishable paths, we add the probabilities. We add the probabilities and not the probability amplitudes. Well, this is the information in the universe, which path the electron has taken. So there is a flash of light. We know, someone knows, there is information in the universe which path the electron has taken. So as long as the universe knows someone in the universe knows which path the electron has taken, either this path or this path, then we add the probabilities. Now, you might ask the question, why does the universe care about this information? Well, this in itself is a fundamental message. At a fundamental level, information might be a fundamental piece of reality as much as matter and energy. As much as matter and energy. So that essentially is the important message. And so where do we go from here? Maybe, just maybe, some of you are not very satisfied with this philosophical approach. Why does the universe care about information about what path or what alternative the electron chose? Maybe you want to argue, maybe the process of observing the electron have disturbed them. Well, there is a photon which bumps the electron, and hence we get a flash of light, and this process has disturbed the motion of the electrons, and that's perhaps the reason why we do not see any interference pattern over here. We just say the probability is being added up. So, is there a way to watch the electrons with a very low intensity light? Dim light. Well, what do I mean by dim light? With a very low intensity light, which has a very low photon flux. So I repeat the same experiment. I have an electron gun. I have my slits. And now my light source is very dim. It's a very dim light source. I'll just say it's a very, very feeble light source over here. So, and now I have again the electrons coming. We don't know what path they are taking because we are just trying to see which path they are taking. So what do we observe? Well, one is that the flash of light is equally strong as in the previous case. So if I get a flash of light, that flash of light either here is equally strong as in the previous case. I also observe that sometimes there is a click on the screen. This is the screen without the light flash. So that's what the dim light does. If there is a flash, we know which path the electron is taking, and the flash of light is equally strong as in the previous case when we did this experiment with a bright light. And sometimes these electrons pass escaping the dim light, and then we get a click on the detector without the flash. So we divide our electrons into three categories. Electrons seen at or near slit 1, we call them P1 prime. Let me also call them seen. They were the ones seen. Electrons seen at or near slit 2 and third is the case because we were doing this experiment with the dim light, electrons not seen at all, just detected on the screen, but we do not know which slit the electrons took. So as usual, we count them, we plot them, make histograms. So what do we observe? Let's say this was a gun. I have my screen. I have the slit 1, slit 2. I have this dim source of light. So let's divide our electrons. This is the statistics for the electrons which were seen. And these were the ones which were unrecorded or unseen. I had the light, but they just go undetected. Over here, I'll get a flash either here or a flash of light here. These are the undetected ones. So now when I make the histograms, I can record the statistics for the seen ones P1 prime, which pass through slit 1, P2 prime, and P12 prime. And I notice that for the electrons that were seen, the probabilities add up. Not very surprisingly, because we made the paths distinguishable. We for sure know which path, either slit 1 or slit 2, the electron took. And then we had no other option but to follow the classical probability rule that if I know for sure what path the electron has taken, what alternatives the electrons are taking, then I need to add up the probabilities over here. So for distinguishable paths, I add up the probabilities. And what about the unseen ones? Well, for the electrons which were unseen, where these paths were indistinguishable paths, my total probability is an interference pattern. So one might say that the process of seeing ends up disturbing the electrons and makes the paths of the electrons distinguishable, and then I need to add probabilities for the electrons that escape getting observed. I recover the interference pattern. So these were the unseen electrons. These were the seen electrons. So one might say the process of seeing, one ends up disturbing the electrons. So this is not very surprising. So what you have seen is the normal wave phenomena. By dim light, I am just reducing the photon flux. So dim light basically means low photon flux. That doesn't change the wavelength of light. That's why the flash of light I see is equally strong. Each photon carries the same energy, just that the number of photons I have per unit volume or per unit area is less. So because the flux of photons is less, there were some photons that were unseen, whose path is still indistinguishable, and I recover the interference pattern. For the ones which were seen, I have disturbed them, and I destroy the interference pattern, I get a probability. Now, is there another way of seeing electrons without disturbing them? Well, think about it. The energy of the electron is, or the momentum is h by lambda. And then let's try to give the electrons, sorry, this was the energy of the photon, a very small kick. That means the wavelength of light I am working with is very tiny. So now I'm working with a high wavelength light, so that the momentum of each photon is really small. It goes inversely as 1 over lambda, and I'm going to give a very tiny bump to the electron. Let's say I can be working with radio waves or something like that, which have a huge wavelength, and this is my slit width over here. So what will happen? What do you think will happen? Initially, when I have a very high wavelength, then I had a probability distribution which was P12 prime. The probabilities were adding up. And then I also came to know which slit the electron passed through. Now imagine I have a switch and I am turning on the wavelength, increasing the wavelength, increasing the wavelength. There will come a time where my wavelength, this is the wave of light, the wavelength of light, that's going to become of the order of the slit width, d. So what will happen there? I'll again lose the information which slit the electron passed through. And why is that so? From optics, it's very clear to you that the resolution of the instrument is related to lambda. The principle of optics, by optics. So meaning, let's say I have some aperture of my camera, which is, the width is d, and I need to resolve 2 points on the screen somewhere. I can only resolve these points. The resolution of points by an instrument depends on the wavelength of light used, or in other words, greater the lambda, poorer the resolution. So that's essentially is the idea, and I'll urge you guys to think a bit more deeply about this, and we can discuss in the subsequent classes. But essentially the take-home message is that, okay, I needed to increase lambda to give the electrons a very, very tiny jolt, but what that was doing was that's going to, if the lambda is huge, then I won't be able to resolve from where the electron came, from slit A2 or slit A1. So in the limit lambda goes to very large, I have no information. I have such a weak observation that I have no information which of the slits the electron took, and then I'll again have an interference pattern. So this essentially leads us to the something you already know in some other avatar. It's just that we are casting it in a new language. Any guesses? What is this principle? I'll just write it down. One cannot, I'll write it down in terms of our experiment. One cannot design an experiment to figure out which slit the electron went through and preserve the interference pattern at the same time. So it's kind of a neat law. No matter what you do, you cannot design an experiment where you would know which path the electron has taken, as well as preserve the interference pattern on the screen. And this is nothing but another way of formulating the Heisenberg's uncertainty principle. So that's kind of neat. Now the challenge problem for you is, let's say, design a very elementary cryptographic scheme. Cryptography is sending secret messages. Cryptographic scheme based on this principle. Well, it's kind of neat. We can actually do this. Just think about it. I have an electron gun, and I am sending, and you have the screen. You are on the screen. I'm sending you electrons. Now, let's say there is an eavesdropper E. This is me. This is you. This is an eavesdropper, which is trying to get the information about what I'm sending you. Now, if the eavesdropper observes the electrons, your screen won't have an interference pattern. And you can immediately conclude the presence of an intruder. So this is kind of fantastic. You and I are sending secret messages. This is me, this is you. And we know that these messages have not been intercepted if this is what I observe on the screen. So as long as I am observing the interference on the screen, I am pretty sure that the messages have not been intercepted or observed by any of this guy, because no one in the universe knows which path the electrons took. That information doesn't exist. So we are guaranteed security by quantum mechanics. So appreciate, this is so different than classically. Classically, you can never be sure what I am sending you is being trapped or not. There's no such phenomena classically. I can be sending you messages and someone would be observing those messages without even disturbing them. Quantum mechanically, as soon as someone tries to interrupt, he would come to know which path the electron has taken, and this interference pattern would be lost. So quantum mechanically, I can send you secret messages and also get a certificate of secrecy, recovering the interference pattern. We'll develop cryptographic protocols more formally, but that essentially is the idea. Quantum mechanics, the observation disturbs the system in such a non-trivial way that you are guaranteed secure communication and also get a certificate of it. So as a last question, challenge question number 2 would be, if quantum mechanics describes everything, which we believe it does. Quantum mechanics is, the universe is quantum mechanical. There has not been any experimental violation to quantum mechanics for the last 120 years since its inception. And we believe that quantum mechanics is the much more fundamental theory than classical mechanics. So the question is that if the universe describes, if quantum mechanics describes everything, then why is it that our bullets, remember the first experiment, do not interfere? So that's an interesting question you can pose to yourself, that I had a double slit experiment and I had a regular gun, not an electron gun, let's say AK-47. It was pumping down bullets, and I got when both slits were open, I got a P12, which was equals to P1 plus P2. Why did these bullets not interfere? So one answer to this question is, of course, that one possible explanation to this question is, of course, that, well, there is information in the universe. Which path bullets took. You know, the bullets might pass through one of the slits and it might heat up the air molecules somewhere here. It might raise the temperature over here. So we sort of know which path the bullet has taken. And once we make the paths of the bullets distinguishable, the probabilities add up. The other explanation is that the de Broglie wavelength associated with the bullet is so tiny, it goes as that even if the bullets interfere, what sort of fringes are you going to get? You're going to get fringes like, because of the tiny wavelength, this is the interference pattern. For bullets, where, you know, this width between the fringes would be of the order of, I don't know, 10 to the power of minus 24. So what you see essentially is an average effect. You see an average effect or an envelope, which you call as P12 equals to P1 plus P2, and the resolution of these interference fringes from each other are so tiny that they are not even observable to you. So a crude analogy would be that let's say you are wearing a blue shirt. What I see is a very average blue color, and my eyes are completely insensitive to the fluctuations, molecule by molecule fluctuations of that blue color. What I get is an averaging out blue color of your shirt. Similarly, even if there is an interference pattern because of the bullet and because of the really tiny wavelength. Like bullet's momentum would be, let's say, 1 Newton meter, and Planck's constant is to the order of very tiny. It's, I think, 10 to the power minus 34 Newton meter or something like that. So uh, the interference pattern you see is so tiny, you're not even able to resolve a minima and a maxima of an interference fringe. All what you see is a average pattern. I'll just color it with the black pen. And hence you're not able to see. What you see is an average classical curve. So the wavelength for bullets is so tiny that any detector cannot resolve an interference pattern. What we see is an average classical curve. Okay, so in some sense, what you can say is that something about the uncertainty principle. We'll just quote our formulation of the uncertainty principle again. The uncertainty principle protects quantum mechanics. Think about it. If we were to find out which slit the electron takes and still preserve the interference pattern, our original argument will collapse. Feynman rules. By original argument, I meant Feynman rules for amplitude addition. Remember, we were adding probability amplitudes as long as our paths were indistinguishable. Now, if we were to find make the paths distinguishable by finding which slit the electron takes, then if we had the interference pattern which implied that there was still an amplitude addition, that leads to immediately to a lot of paradoxes and the way we formulated the problem. So in some sense, the uncertainty principle is protecting quantum mechanics. It says that the moment you make the paths distinguishable, you know the electron is passing through one of the slits, then you have to add probabilities. You cannot get away by adding the probability amplitudes. And frankly, no one has ever found a way out of this. To detect which slit, that is, to detect which slit the electron passes through and also preserve the interference pattern. In fact, as we discussed, Heisenberg thought that this must be a law of nature. And we've already based our cryptographic scheme on this law of nature, which is secure, guaranteed by this law of nature. The more formal way of formulating the Heisenberg's uncertainty principle you already know is delta x delta p greater than or equals to h bar by 2, or one cannot determine position and momentum to arbitrary accuracy. This is fundamental and inherent to the theory. We've just formulated a information theoretic approach to it, that we cannot have the information about which slit the electron takes as well as preserve the interference pattern. So we have given an information theoretic formulation. So that ends essentially this lecture, and I'll be putting on some homework assignments rather soon. Thank you.